Hi, welcome to my talk. This is Improve Your Embedded Hardware, IoT Hardware Today. Make your Rev A hardware count. My name is Chris Gamble, and I really appreciate you being here. I know you have a lot of choices in the Embedded Online Conference, and I appreciate you actually taking a little bit of time to do this here. So let's take a look at the slides here as we go along. All right, a little bit about me first. My name is Chris Gamble. I am the Developer Relations Lead at Goliath, and I've been doing hardware quite a long time, about 20 years, coming up on 20 years, in places like ABB, Samsung, Splyframe, Keithley, and Hologram. And I've also done some consulting out on my own, which I really enjoyed. That's what I was doing right before I came to Goliath. So we're going to be talking about Rev A hardware today. And let's talk a little bit about who this talk is for. First off, it's about people that are building early stage IoT hardware. So you might be out there, you might be an embedded person building some stuff that's not connected. You might be thinking about making it connected. And some of the stuff kind of changes as you are moving stuff online. And that's kind of some of the things we're going to be talking about here today. So I'm assuming you are building early stage hardware, and you're probably in this group here somewhere: firmware, hardware, cloud, and IoT. And I think there's an important thing here that all of these people, even if you're just one of these people, maybe you're multiple in your company, all of them are stakeholders though, and that's an important thing. So you need to be thinking that even if you're, maybe you're doing both firmware and hardware, but you might be working with a cloud engineer, maybe you're just doing hardware and you're working with the other two. There's kind of a mix here, but these are kind of the three different personas that I imagine that are out there. There's kind of three job requirements that are taking on these projects here, and you might be one or more of these. IoT hardware itself is often simple in its execution, right? There, a lot of the IoT applications, at least, are, and the functionality is often simple. It's take a reading, send it to the cloud, right? Or send something from the cloud down to a device, unlock a door lock. That's a very common thing here, and that by itself seems simple, but it's really the putting it all together, and that's what's really not simple here. I think I already showed it on my desk by accident, but this is going to be the hardware that we look at. I'm showing you this now simply because when I'm a hardware engineer, and if I don't see hardware within the first couple minutes of a presentation, I start getting a little sleepy-eyed. And so I wanted you to know we are working our way towards a case study, and specifically a case of hardware here too. And so we will be talking about hardware towards the end, but we're going to talk about some of the things that kind of lead up to actually building out the hardware here. And so let's dive in and start talking about this. So we're going to be talking about Rev A, right? That's kind of the thing that we're getting back to here over and over again. We're going to be talking about Rev A and how things are impacting you in Rev A. So let's talk about Rev A. Actually, let's talk about before Rev A. Before you even start at all, you need to be talking to those other three people. So I'm just going to be talking about myself here as a hardware person, and I'm going to assume I'm working with a firmware person and a cloud/IoT person. So I'll be the person that's doing the hardware here, and we're going to talk about how I might be interacting with some of the other folks that are involved. One of the most important things is that you are talking to those other people, and you're talking to them from day one. I've seen in past companies that people say, we'll just, we're going to go throw together a prototype here, and we'll just try it and see what happens. And the impacts of choices on that first day can just ripple all the way through your, all the way to production, all the way to a problem you might have sometime long in the future. And it's important to kind of understand how these things work and how the interaction between these different groups really can impact your decision making. One thing that's really important is to do some of that goal setting. It doesn't have to be any kind of formalized process, but taking a second over lunch with your two coworkers. If I'm the hardware person and I'm talking to a firmware and a cloud person, what are we trying to get out of Rev A? What are we trying to actually achieve here? Again, it's conversations that sometimes don't happen. And I think another thing that's important is, what are some of the constraints that we can just let go of? One of my former errors that I've made many times in the past, and I'm sure will make in the future, is I try and make the tiniest board as possible from that first rev. And it's miserable. You're probing and you can't access stuff. You had to make trade-offs because you leave signals off a board, and because you don't have space to run all the traces. And and just thinking about how that ended up rippling all the way through the Rev A, and we weren't able to get as much out of the design as I wanted. And that's a shame from a money perspective, especially from a time perspective, and from a teamwork perspective too, right? Because it's frustrating because I didn't have access to one of the buses that could have been helped to, maybe could have bodged wires on there and made it a little bit easier there. So if we're trying to get the most out of Rev A, I think it's really important to think about what are some of these trade-offs that allow us to really do as much as we can with this first piece of hardware. Cost is another clear one. If you're super cost constrained, it really changes a lot of your trade-offs that you have to make in your first rev and really all of your revs. And I think it's an important thing to know, but it's just something you have to think about up front. Another thing is, how many are you really going to make? This might be tied to your cost as well. If you're trying to go to production with your Rev B board, you might be much more conservative in what you're trying. You might take a lot more time on your planning. And I used to work at a company that took 6 months to do the first rev, and it just because the board itself was really expensive and you had to get everything right within 1 or 2 revs because you didn't have all that many revs. So it's really important just to know all this stuff. And the last thing is that you are setting these goals. I said it doesn't have to be a formalized process, but I do think it's really important to have a test plan, right? So write stuff down. Write down, you don't have to have a formalized process about like sprint planning or anything like that, but what are the things that you are, when you figure out what you're trying to get out of this rev, write them down, and then you'll be able to review them later. That's a really important thing here. All right, let's talk about what happens in the hardware side of things, right? So what do you have to think about, and what can you do to get the most out of it? Let's broaden the scope a little bit and think about not just me as the hardware engineer now, but kind of all of the stakeholders. What are we doing to make this hardware better? And I think one thing that's really key here is design reviews, right? And that means it's not just going to be the hardware engineer that is doing a design review. You really need to be coming to this design, maybe it's the conversations before a design review, but really the ultimate thing, hopefully you have multiple design reviews as well, but when you're coming in as a cloud engineer, firmware engineer, hardware engineer, what are some of the things that you should be looking for to ensure that you are getting the most out of this Rev A hardware? First thing, let's talk about some flexibility. So as a hardware engineer, I really like to have multiple footprints on a board. I think that in the era of part shortages, that is critical. It allows you to have more options there. Obviously, you do need to have a larger size board in order to fit more stuff onto it, but it's always easier to leave a footprint not populated and mark it in a schematic or take the parts off a board if you already do populate it, to be able to selectively populate different parts of your board. Really, really important there. Another thing is, if you have space for it, I think kind of standardized interfaces also can really help you here, because then you're able to swap things out kind of on the fly. Maybe not hot swapping, maybe you're not doing while the board's powered, but that's not really a requirement. It's really about like being able to plug in a new sensor, try that out, run some experiments on it. Maybe that doesn't work, maybe it does, plug on the next one. And if you have standardized interfaces, you can start to do that sort of thing. So one thing that you'll see in a later thing is the click bus is kind of a quasi-standardization from a company called Microelectronica. They make all these different modules there. PMod's another one that's popular in the FPGA space. There's Stemma and Quick, or these I2C kind of cabling capabilities. And that allows you to plug different things in and try them out, and ultimately, even if you can't buy them off the shelf, which is a best case scenario, I think, you could go and you can make something of your own and plug that in and reuse that standardized interface. Often it's going to be things like I2C buses, SPI buses, things that are not necessarily the specific GPIO orientation, but having that flexibility there can be really, really useful. And then I put configuration options and in situ measurements, and this is kind of an abstract way of saying 0 ohm resistors. I love 0 ohm resistors. I put them all over my board. Oh man, my face is blocking. That says everywhere, of course. I think that they are probably my favorite component, because I'll put them, across RX, TX lines in case I swap things. I'll put them if I want to measure current through stuff. I want to tack wires on for measurement later. Really, my Rev A boards have 0 ohm resistors all over the board. And if you are a firmware engineer and you're looking at your hardware engineer's board and you're like, wait, where are the 0 ohm resistors? Ask about that. Suggest it. I think it's just it is a important thing to have on your first prototype here. Visibility. So this is another one where LEDs can, when you don't have much insight into what's happening inside the silicon that you're playing with, an LED is going to be the light in the dark, so to say. And I think that having a range of different LEDs for statuses, for indicators, for pushing out coded messages, even if you need to, if you're really in a tight spot, I think those are key, and having a lot of them on board is important. Test points is another one where you need to be able to get at the different signals and have them very clearly labeled there so that you know specific outputs when you're on your test and measurement equipment and stuff like that. I think screens, if you have the time and inclination to do that sort of thing, I think screens are a great way to kind of have heads up insight into what you're looking at inside the hardware you're playing with. Even if they're temporary, right? They might be plugged into those standardized interfaces. You can always pull them off later. And then finally, extra UARTs. I think that's really important there, and they're accessible too. That's another thing. And let's talk about accessibility. I think accessibility as kind of a broad topic when you're doing design review, making sure that you can get at the programming headers, making sure that you have large pins to solder to if there are bodge wires necessary, right? Especially if you've got fine pitch parts that you can't see all the signals underneath, you want to make sure those are broken out. They have big pads there. Again, this is kind of built on the idea that you have a lot of space in your board, and if your hardware engineer says, I can't fit this stuff because we're trying to fit this stuff inside this tiny little case, if that's not a true requirement, I'd say ask them, can we go bigger? Can we have this very, very large accessible board so we can try all these different things we're trying to do? And Rev B can be that shrunk down version. So that's an important thing there. And finally, clarity of documentation. I think that it's really important to have stuff on the schematic, clear numbering system, clear pin names, standardized pin names, things that make sense, that if you're looking at it, you should be able to read a pin name and it's not ambiguous. RX and TX are well labeled. I take on the RX from _ TX2 sort of things, that you're verbose in your labeling of things, and hopefully very accurate as well, right? Make sure you go, if you are the firmware engineer, you're not only checking that the label is very verbose, but that is correct. And then finally, marking stuff on the PCB as well. I think that's really important here as well, right? You got to make sure that you can actually see all the things that are happening here. All right, let's talk about the firmware side of things. Now, firmware is usually the responsibility of the firmware person, if you have one, or if you're doing kind of multiple duties here, you have you're in charge of multiple things here. But it's important to kind of talk through kind of the implications of things. And what I'm going to show here is actually very tied to the hardware, most notably the hardware choice, right? So when you're choosing your main parts around micros, and I'm really going to focus on micros here. Micros, though, and your communication mechanisms and your sensors that are out there, all of this stuff is going to interplay with your hardware design, and it's going to kind of feed back on itself. And as a hardware person, I wish I would have taken the firmware persons, when I was working with firmware people, not doing the firmware myself, I wish I would have taken their insights into effect, or into my planning more often. Often I was kind of playing in the specsmanship game and saying, oh, well, vendor A has this part and vendor B has this part, and I really care about these peripherals, but not thinking about the rippling choices throughout, like I mentioned at the beginning of this talk. It really does have a really big implication, and that's because each of these different parts might have a different RTOS available for it, right? So real-time operating system. When I say RTOS, you might be saying, oh, well, I work in bare metal, and that is fine, but generally, very broad generalization here, when you're in the IoT space, you're going to be moving, you have more stringent timing requirements, you need more complex interrupts. You might be working with a two-chip solution where something else is doing all the communication. That's fine, but I'm going to focus on the things that are using an RTOS, and so here are some common options here. I use both FreeRTOS and Zephyr. ARM Embed was one that was that is still out there as well, and there's definitely other options, ThreadX, and I guess that's called Azure RTOS now. There's lots and lots of different options out there, but one thing I do want to call out specifically is that an RTOS is often different than the ecosystem. Again, this plays back kind of how firmware is tied to the hardware and how that kind of ripples through your design. So what we're showing here is RTOS, but what it often is the ecosystem, right? So Zephyr is one of the more rare ones where the Zephyr ecosystem is both an RTOS and an ecosystem because of how it was set up and started as open source project, and there's a lot of different vendors kind of contributing to it. But with FreeRTOS itself is not an ecosystem, but many of the vendors take the FreeRTOS and put it into their ecosystem. So one example is ESP-IDF from Espressif. They build on top of FreeRTOS. Same with Modus Toolbox. They have FreeRTOS in there. SD has their own FreeRTOS. ARM Embed is another one that actually Embed was the ecosystem. Embed OS is the RTOS, so it's important to kind of think about how this stuff ripples through your design, because then this impacts all of the support and the availability of drivers that you might have. Drivers, support, networking layers, all of the things that are going to impact the rest of your firmware stuff, that's all driven from that hardware piece and how that kind of ripples through your design. Now, we're talking about an important Rev A. There's probably nothing more disruptive than choosing the wrong microcontroller in an embedded project and then having to start over, right? It might just be changing out a footprint for the hardware person, but it might be ripping up tons of code and reporting to another device. So another thing could be portability. Something like Zephyr does port to multiple devices, but if you're in ESP-IDF and you decide you want to switch to Modus, that's a big deal, and you kind of have to go and port a lot of the capabilities in what you're doing there. Not impossible, but not easy as well. Another thing is going to be abstraction layers and peripherals. So this is going to be things like, how are you communicating with all the sensors that you have on board? What are the capabilities of your part? How does that impact your implementation in firmware? And then how are you talking to all the things that are outside and around your device, like sensors, like communication things, if you have an external modem, things like that, and even troubleshooting abilities too, right? So like where are you UARTs? How are you getting stuff in and out of the processing parts of your IoT design? Finally, pin planning, right? Once you know what's available to you, you need to actually talk about where and how those signals are going to be used, all those peripherals are going to be used. And then when you have a critical bus, right? So say you have a really important USB, you need USB 3 on your device. Well, you better make sure that you prioritize with your hardware person that these capabilities are being used on the pins, that if there's extra interrupts that are needed, maybe there's external parts that they have to interface to, but really just thinking about how some of the functionalities in the firmware space ended up impacting back to the hardware space. And again, trying to minimize that disruption, because once you make some of these decisions, it becomes hard, not impossible, hard to backtrack. And if you do, I am very, very, very encouraged by all of the chip vendors that are out there that are making GPIOs much more flexible. They kind of have these crosshatch kind of ability to reassign pins. That is amazing, but some of them always have these kind of little asterisks up in the corner, and make sure that you understand where there's an asterisk, because that can be problematic for your design. All right, last piece for the planning piece is the cloud design. All right, so you might have a person that's actually working with you that is a cloud engineer or an IoT engineer. There's a lot of different titles out there. Usually it's someone that's actually focused more not on the databasing and all this stuff kind of out in the world with software engineers. They might be kind of doing dual duty there, or it might be you. You might be in charge of actually getting this stuff up to the up into the cloud, and that's an important task to take on as well. It's something not to take lightly. I often took that lightly as a hardware engineer, moving into firmware and then learning cloud stuff. I was often like, I'll just throw a message to an MQTT broker. It's so easy. And let me tell you, folks, it's not easy. If you're coming into the IoT space, there's a lot to think about there. I think one thing that's really important is to think about, can you send an OTA update? This is an important thing to me, not just because of the kind of work that I do now, but also because thinking about the failures that I've had in my connected devices in the past, it was almost always tied to the fact that I left something to later where I said, you know what, I'm going to field test. I do Rev A, I do Rev B, it sits on my desk, I get to Rev C, and I'm like, now I'm ready for field testing and getting out to the hands of the customer. or hands of the user, or testing it even just unplugged from my serial terminal. And when you unplug from your serial terminal and you start moving out into the world and you are no longer able to access that device or play with it, you enter an entirely new world of pain. And if you can't send an update to that device, and if you can't do that early on in your Rev A, specifically in your Rev A, I think you are doing yourself a disservice, because you're missing out on much of the testing that will ultimately prove that you're getting the most out of this Rev A device. And if you're not getting the most out of this, if you're not leaving your desk with Rev A, you're not getting the most out of this device. So if I could say one thing, it's just get your Rev A out in the world. Get it into your users' hands, even if they're just a different coworker that's not working on the project. It's most important there. And I think the most important thing tied to that is being able to do an OTA update so that you can go and fix some of the problems that you discover there. Another thing that's important to think about is kind of where's your data, what is your data, of course, right? That's kind of usually pretty well thought, again, thinking about these simple IoT applications. If you're reading a sensor, and the sensor, so like an air quality sensor, which we'll look at a little bit later, if it's reading CO2 readings, it's pretty obvious that I'm going to send a CO2 reading up to the cloud. Okay, but now where is that data going on the cloud? How is it being formatted? Where else does it need to go once it gets there? And how does it need to be formatted or reformatted or transformed and all that kind of thing. So you need to be thinking about that early on, because that also then ties into where is the processing happen. In this very, very simple example here of just CO2 data, do I need to format it on the device? Can I send just a raw 34? What does 34 mean? Well, maybe I'm going to do that on the cloud. Maybe I'm going to do that on the device. Do I need to add units with my data going to the cloud? Another thing is kind of where is calibration happening, right? Sometimes calibration happens on the device. Sometimes it happens on the cloud. Maybe you don't need that context to be local. And it's just an important thing to know, because that's also going to lead into how much time and effort you need to spend on that Rev A device and the complexity of the code that you're writing to put on there. How are you going to be able to access that data? So now you've sent the data to the cloud. You want to get it back off of there. And what are your access methods? What is your testing of that data? And how much is that? Maybe that's not actually important to you. Maybe it's, as long as you know that the data is there, that's enough for you. But if you're doing things right, and that's air quotes there, if you're doing things right, you're out in the field and you're actually interacting with the data and the user, and you're trying all these different functions out. And I think in order to do that all the way, you need to be able to have an interface to that data from some external device. Again, your test goes best when you're no longer plugged into the serial terminal, because I think that's the most realistic use case. Your device is going to live out in the real world eventually. I think it's best to pull that forward and do that as soon as possible. Okay, let's talk about some of the testing and what's happening during Rev A. If I haven't made it abundantly clear yet, I obviously want to get the most out of this as possible, right? I want to make sure that you are trying to squeeze every last drop of usability out of your device in Rev A. And some of this takes the form of just testing on the bench, right? This is an important starting place for any hardware project. I'm a hardware engineer. Oh, I'm blocking the, let me move my face here. I'm blocking some of this stuff. And I think that this comes down to, good tools. I'm a big fan of the PC Bytes. I don't know how you say that. Especially as part sizes keep shrinking, it's important to have accessibility to different test points. This is showing it's broken out to small test points, but even still, it's important to be able to then access those in a reliable, repeatable way. I think this kind of stuff is really important here. I use things like the Salier and the Analog Discovery 2. I really like the portability. If I'm testing stuff out in the field, I want to be able to pull out these devices and test things. As soon as users tells me that there's a problem as they're walking down the street, I want to be able to plug it into a device here, and those things are portable for that sort of thing. And finally, IoT devices are almost always based on batteries. Not always, but often have a battery component, and I think things like the OT, ARC, and the Joule Scope are really important for being able to do some performance testing, right? You need to be able to actually understand how your battery life is working, and I think these portable devices really make it possible to be working out in the field. Another thing that's really useful here is power on self-test. I think, I'm showing, of course, a BIOS screen here, which was my Google image searching was not, it's not easy to show this kind of stuff. But I think basically being able to understand at boot up, having a standardized test suite that things run through. Again, if you have a screen on it that even if temporary during testing phases, you're able to see that, yes, the power supply came up. Yes, all of these different internal tests ran so that you're confident when you're handing it to the person doing the Rev A test out in the world that, yeah, they should go and use it for the functionality and testing and moving stuff forward. In terms of configuration, again, you're going to be trying a lot of different things here, and leaning on configuration tools can really help you to try out a lot of different things. You can, of course, always do this stuff in code, but having some kind of interactive configuration can really help here. I am in Zephyr quite a lot. I'm a big fan of Zephyr, and I really like they've adopted menu config, which is from the Linux world. That stuff allows me to go and kind of tweak different characteristics within the device, and that's really at the kind of the kernel level, but other things like being able to interact with devices over sensor shells, over different shells that are available as well. Interactivity with these things that are out in the world is really, really important, and I think being able to build that in, leaning on tooling that's already there, can really help you out. Other configuration tools, this is something that my company Goliath does. This is a setting service. So when I have a connected device, it is connected to the internet, I can go and push things down to the device, like calibration, like settings, like I might change how often it's transmitting, how often it's some calibration type stuff like altitude as shown here, offsets, things like that. Because again, when you're out in the world, you don't have time to go and plug that USB cable in to change stuff over serial. So then how are you going to be able to do that? Having some tooling to do that's really, really important for getting the most out of your device, your Rev A. When things go wrong, I find that it's really important to have kind of a concept of where things are going wrong, and I often lean on the OSI model. And so this is probably a little bit too abstract here, but ultimately I'm kind of just going through, I'm usually going from bottom up. If things, well, actually probably top down. It could depend on the day and what the problem manifests as, but like, things that are really simple at the physical layer. Is it turned on? Of course. Is it transmitting? Are the LEDs on? I put LEDs on the board. Are the LEDs on? And then, so that's more if I'm seeing some device problems. Is the self-test working? That sort of thing. Am I getting connectivity? So we'll go through some of these tools that actually allow you to do that sort of thing. One of them, if you're having networking errors, I didn't put a label on this one, but this is Wireshark. And throughout the networking stack, it can help, especially when you're kind of in that middle of the stack, the OSI layer, OSI model. When you don't know where that packet's disappearing, Wireshark really helps with that sort of thing. I think another one, obviously debugging. When you are still at the bench, it can be really important to understand where you are in your code. But then I think another layer here is that if you are doing an RTOS, having some thread awareness. I use Segger Ozone for this sort of thing, but being able to understand where you are, where you're kind of getting lost in the shuffle is really useful. Again, with an RTOS, because you have multiple threads going on, System View, this is another Segger product. I use Segger System View to kind of understand more about that, especially if I'm using things like that Joule Scope or OT Arc to do power measurement. I want to kind of know, where am I spending my time? How long am I in sleep? Where am I in sleep? Is it actually doing what I think it is under the hood? Having multiple ways to visualize this stuff is really useful. I think when you start to have connectivity problems, for when I'm doing cellular stuff, often, if a packet's not getting somewhere, I have logging, but if I don't have cloud side logging, then I don't, and I'm not plugged in, well, am I getting to the actual network? Is my cellular device actually connected? Can I see it at the cellular location? Is it hitting a tower? That sort of thing. Again, just another tool in your tool belt here. And then finally, another Goliath thing, remote logging is kind of the most important thing for me day to day, because when I'm not plugged into a USB cable, or your UART rather, when I'm out in the field trying to get as much out of this Rev A as possible, I want to be able to see all of the same logs that I'm seeing down on the device. And again, from a cost perspective, I might really care about not sending all of this debug data when I'm in production, but because it's expensive, both in battery and in data costs. But when I'm in Rev A, cost is one of those things where it's got to be squishy when I'm doing a prototype. I don't have to, I have to spend a little bit more money in my prototyping stage, and definitely sending all that data through is really important. Finally, another one is just kind of the stuff that if I'm not making maybe final app that a customer is using, I still want to be able to visualize that data. And so this is just showing like a simple way to visualize some of the data that's coming off the cloud here and being able to dig into it, really see what's going on here. This is actually Grafana. This is, again, the air quality monitor that we're going to look at here. This is how I visualize it and actually see what's going right and wrong here. Or even if there's just no data showing up, that can be another good indicator of what's of the fact that there's a problem here. Okay, so you've gotten through all of your Rev A testing, you've gotten out in the field, you think you're at the point of that you've run through all your different tests, you check your testing plan, of course, and you make sure that you actually covered everything that's in there. And this is where I will call out once again, you did have a testing plan, right? Because if you thought at the beginning, well, I'll just kind of figure it out, there's no big deal, I know what I need to be testing here. If it's not written down, you don't really have a testing plan. You don't really know what did or didn't go right, and you don't know whether you've squeezed everything out of there. You might even add stuff later that you didn't think you wanted to test, but you add it to the testing plan, and like, we discovered this and we need to look at this, because then that might also contribute to future testing to make sure that you've actually covered it when you have changed your Rev B board. And that is another important thing, capturing Rev B changes. I think it's really important to having some kind of standard way to do this. I often do this in my my GitHub repo for the circuit board. I think that's a great way to capture stuff, is just issues. You can resolve them once you change stuff. As you commit a change, you can obviously refer to the issue and say that it's closed, and it'll automate and stuff like that. I really like that. Other people do it a lot of different ways. It could be a spreadsheet, it could be however you want to do it, but it's important to do that. And then once you've done this, it is finally time to start your next rev. And that is always an exciting time, but I think it's important to be measured when you're deciding to do that next rev, because there is often significant time cost and money cost. Okay, so I'll put my hardware up on screen as opposed to my face here. So this is some of the stuff we're going to be looking at. We can look at it a little bit closer here, but we do have some slides around this as well. So one question I asked is, what does hardware look like if it's perpetually at Rev A? And this is kind of a silly question to ask, because most people aren't at Rev A perpetually, but I often am, and I'll talk about that a little bit more here. And so I think it looks like this, right? So this is the Aludel, which is kind of the baseboard, and then the Ostentus is that top cover, that PCB faceplate here is called the Ostentus. And let's talk about some of the specs that I put into this thing. So it's based around a Feather form factor, which is a dev board form factor. So not a chip down solution with like a micro or a SIP or module or anything like that. It's actually another layer on top of it. Then I also have an abstracted 2 microbus click headers. So you'll see that in a second here. There's an interstitial PCB, that's the Aludel Mini, I call it, that actually is what glues those things together and has some other stuff in there like power. There's also additional abstracted headers using Quick and Stemma, which is basically just I2C and power. And then there's a standard case form factor here with standard inserts. So we do this because the stuff that I'm doing, I'm trying to make a lot of different reference designs and swap out a lot of different hardware. I'm kind of doing Rev A every day, right? Trying to not only try out a new sensor or new idea, but then also put it out in the world and see what goes right or wrong with it. So it's not just making an asset tracker and making sure it connects to the GPS, but then actually walking around outside, and can I get all the data, and can I pull it back in, and is it accurate, and does it look good, and can I see this kind of stuff on a visualization platform like Grafana. The other thing I like is it allows me, again, my Rev A's might be a little bit different than other people's, but I need to be able to swap out micros and sensors and displays, because I need to be able to show interoperability for the cloud platform that I help work on, and show that it works on all this different hardware. And it's important to note that this is not a commercial deployment, right? So like if I put this thing out in the rain, this box, it would go very poorly. It's not watertight. It's not. It's more for flexibility than it is for actual usability in like a real world context. But I think you can often get around some of the stuff that are going to be your eventual constraints. And I think it still has, what I'm often proving out is kind of the concept of collecting data in a certain way versus actually collecting that data for months and months and months like a normal IoT engineer would be doing. It means that we're basically like a dev I'm making kind of this thing I'm showing here is more like a dev platform. I I think some of it might be, like I said, it's not waterproof. It's over-indexed for swappability, so that I can have these different. These are like the plates that go in there and have different inserts, so that I can have different dev boards or different sensors. It might be over-indexed for swappability, but ultimately, even though it is missing some of the kind of like the longer-term constraints, I think it actually still approximates what a lot of engineers do for the Rev A, right? You're often trying to prove out a capability, and you're trying to understand, will this idea work, and then ultimately take it to that next stage and get the most out of it. One thing that we did with the Ostentis, which is the display board, we really wanted to have a display on there so we could see this heads-up data as we're walking down the street, be able to cycle through it. It's actually got cap touch on there, so you can cycle through different readings. It's got e-ink, so you can see the readings out in the world, that sort of thing. But it's also got an RP2040, which is like a board that I would never use in production. It's got the Pico rather, which has an RP2040 on it. I wouldn't put a Pico in production, right? But I might put a RP2040, or I would go chip down at least. But that worked out for me, right? This is another kind of dev board way of proving out this idea and interfacing with it, and making sure that we can make it maximally flexible. Again, it might not be something that you're thinking about here, but it is something that was very, very useful for my testing. Let's see if I can find the camera for it. Come on, Chris. There we go. So just to see it here. So this is kind of the interface. You see that this does kind of have a different plastic look here, but from far away it's kind of hard to see. Even when this is off, it does have a display. These touch panels are all, actually I could probably just turn it on. Let's see if it lights up. There we go. When it lights up, it does have different indicators here, and I can go and change things like that. I can cycle through different readings, and so it is interactive in that way. And again, this is for going out in the world and being able to walk around. And so like I know right now that it actually is connected to the cell network. It is connected to Goliath. It is powered on. And then this is just a kind of a busy light as I'm cycling through things here. It's a little out of focus. Sorry about that. That's worse. That's much worse. And then inside the box, it is just a set of standard interfaces, right? So it's just these are just click headers, and it's got a battery here. There's the feather form factors down the bottom, power switching here, buttons, interfaces like that. So it allows us to have maximum flexibility while also playing with lots of different concepts here. All right, let's see if I can get back to the screen. Some things that didn't go well based on some of the constraints that I kind of talked about is that accessibility, right? So the programming header is actually kind of shoved in the bottom of the board. Once I put this thing into the box, I can't get at the programming header anymore. So everything has to go over OTA after this. This is just this is a trade-off I was willing to make because I needed to fit it all into a case here. But again, it's going to come down to what you need in your design. I probably over-index for space savings as well. I think that even though this is a flexible design, and I talk about having a lot of different capabilities in different boxes here, I was still trying to keep it relatively small, even though it has this maximum flexibility here. Not always the most realistic thing, but I wanted it to look good because it's a Rev A, but it's also a showcase platform for the stuff that I'm doing. So let's talk about though what would happen in Rev B, right? So I'm in Rev A currently. This is perpetually in Rev B. What I would do if I was taking it to Rev B, oops, there it goes. If I was taking it to Rev B, I would definitely get tons and tons and tons of space savings, right? So all of these standardized headers that I show here, like all these click things, this is like a teeny tiny little sensor on here that I could just put that on a board. It doesn't need all this other space here. Same thing with like the vertical height. All of this would be constrained down a lot. And so in that way, I have blown this up to a much bigger thing. I could have made a tiny little board for a Rev A, but it wasn't necessary, and then I lose a lot of that flexibility that I wanted. I would have had more pins available. So one of the big downsides to doing this sort of thing, using a dev board in this Rev A proof of concept kind of form factor, is that even though so I use the NRF 9160 SIP quite a bit, which has tons and tons of pins, but they're not broken out on the feather form factor. It's only got like 28 pins or something on it, so there's a bunch left behind, and I don't have those broken out there. Again, that's a trade-off that I was willing to make, but for I would get access to those. I would have more capabilities once I actually put the SIP down on the board. So that's an argument for doing that sort of thing. And finally, I would be able to get down to a single board layout, and I'd be able to cost optimize, and I'd put in a watertight enclosure as well. Oh, and power optimize. All right, so I'm running out of time here. This is something that I do every day. We publish about it on our blog, the Goliath blog. Please come and check that out. And if you'd like to find me online, you can always do that here. I really appreciate you attending here today. If you have any questions about hardware, firmware, any of that stuff, I'm always online. I love talking about this stuff, and I'd love to talk to you about it more too. Thanks so much for attending, and I hope to see you somewhere on the internet.